Hello everyone. This is Qi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Welcome back to our Deep Learning course. Today, we're continuing Chapter 5, Classic Convolutional Neural Networks 2. And our focus is Part 5.2, AlexNet, a landmark model that revolutionized CNNs. Let's start with AlexNet's structure, its innovations, and then use it for a practical task, Chinese font recognition. First, let's get to know AlexNet. It was designed by Hinton and his student Krajewski in 2012, and it won the ImageNet competition that year. Most importantly, it was the first model to use convolutional neural networks in the ImageNet contest, proving CNN's power for large-scale image tasks. AlexNet has a total of 8 key layers. With a clear flow, it starts with alternating convolutional layers and pooling layers, convolution pooling, 3 consecutive convolutions pooling, then ends with 3 fully connected layers, the output layer. The diagram on the slide shows the dimension changes. Input is 224 multiplied by 224 multiplied by 3 color image, and after each convolution or pooling, the feature map size shrinks like 224 55 27 13 6, while the number of channels increases like 396 256 384 256. This balances feature extraction and dimension reduction. Let's zoom in on the structure diagram to confirm each layer's role. First convolution, 11 multiplied by 11 kernels, 96 total, with stride 4. Output 55 multiplied by 55 multiplied by 96. First pooling, 3 multiplied by 3 max pooling with stride 2. Output 27 multiplied by 27 multiplied by 96. Second convolution, 5 multiplied by 5 kernels, 256 total, with same padding. Output 27 multiplied by 27 multiplied by 256. Second pooling, same 3 multiplied by 3 max pooling. Output 13 multiplied by 13 multiplied by 256. Then 3 consecutive 3 multiplied by 3 convolutions, 384,384,256 kernels. Same padding, keeping 13 multiplied by 13 size. Third pooling, output 6 multiplied by 6 multiplied by 256. Finally, 3 fully connected layers, 4096, 409, 610, 00, 4 ImageNet's 1000 classes. The max pooling labels on the diagram clearly mark where downsizing happens. This is key to AlexNet's efficiency. AlexNet's success comes from 6 major innovations. Many are still used in modern CNNs. First, ReLU activation. Replace traditional sigmoid or 10H with ReLU, solving gradient disappearance in deep layers and speeding up training. Second, dropout randomly ignores 50% of neurons during training, preventing overfitting by avoiding over-reliance on specific neurons. Third, overlapping max pooling. Stride is less than pooling window size, for example, 3 multiplied by 3 window. Stride 2, capturing more spatial information than non-overlapping pooling. Fourth, local response normalization, LRN, normalized feature maps locally to enhance generalization, later replaced by batch normalization, BN, for better results. Fifth, GPU acceleration, used CUDA to leverage GPU computing power, making deep network training feasible. AlexNet couldn't run on CPUs back then. Sixth, data augmentation, expanded training samples, for example, image flipping, cropping, reducing overfitting on limited data. These innovations laid the foundation for modern deep learning. Now, let's use AlexNet for a practical task, binary classification of Chinese fonts, distinguishing Lishu and Xingkai. First, data preparation has 2 key points. Task type, it's a binary classification problem, only 2 classes, Lishu and Xingkai. Directory structure, the data must be stored in a fixed way, under /data_, Alex or Chinese style /. There are train and test folders. Each has Lishu and Xingkai subfolders storing corresponding font images. The ls commands on the slide confirm this structure. Keras needs this to automatically read labels. Next, we build a data generator, a special way to read data, crucial for large datasets. Here's why we use it. Principle: instead of loading all data into memory at once, which would crash if memory is limited, it reads small batches of data on demand according to the directory structure, and does pre-processing, like normalization, on the fly. Trade-off: it takes a bit more time since it reads data batch by batch but lets us process very large datasets with limited memory. Tool: we use Keras Image Data Generator. This function handles batch reading and pre-processing in one step, which is perfect for our task. Let's write the data generator code. First, set im size equals 227, AlexNet's input size. Then, training generator, train underline, generator equals image data generator, rescale equals 1/255. Flow underline, from underline, directory. Rescale equals 1/255 normalizes pixels to 0 to 1. Target size equals 227. 227 resizes all images to 227 multiplied by 227. Batch underline, size equals 200 reads 200 images per batch. Class underline, mode equals categorical means one hot labels. Validation generator, same as training but reads from the test folder. This generator automatically maps folder names Lishu or Xingkai to labels. We don't need to manually assign labels, which saves time. To confirm the generator works, we visualize 10 sample images. Use x, y equals next validation underline, generator to get one batch of data, x equals images, y equals labels, then create a 2 multiplied by 5 figure with matplotlib, loop through 10 images, display each with ax, I. Hem show x, I. The slide shows the result. You can see Chinese characters in Lishu and Xingkai styles, with clear font differences. This confirms the generator is reading data correctly. Now, let's implement AlexNet for this binary classification task with Keras. The code follows AlexNet's structure, adjusted for 2 classes. First, input layer, input 227,227, 227 multiplied by 227 color images. Second, first conv pool, conv 2d 96, 11, 11, strides equals 4, 4, activation equals relu, max pooling 2, d, 3, 3, strides equals 2, 2. Third, second conv pool, conv 2d 256, 5, 5, padding equals same, activation equals relu, same max, pooling. Fourth, 3 convs, conv 2d 384, 3, 3, padding equals same, activation equals relu, twice, conv 2, d 250, 6, 3, 3, padding equals same, activation equals relu. Fifth, third pool, same max pooling. Sixth, fully connected plus dropout, flatten, dense, 409, 6, activation equals relu, dropout, 0.5 twice. Seventh, output layer, dense, 2, activation equals softmax, 2 units for 2 font classes. Finally, model. Summary prints the full structure. Let's analyze the model structure from the summary output. Conv layers, for example, the first convolution, conv 2d1, has 34,944 parameters, 11 multiplied by 11 multiplied by 3 multiplied by 96 plus 96 biases, and outputs, 55 multiplied by 55 multiplied by 96. The 3 middle convolutions keep 13 multiplied by 13 size with same padding. Pool layers all have 0 parameters, no training needed, just downsizing, for example, max underline, pulling 2d underline, One goes from 55 multiplied by 55 27 multiplied by 27. Fully connected layers. The first dense one has 37,752,832 parameters. 6 multiplied by 6 multiplied by 256 multiplied by 4096 plus 4096 biases. Most of AlexNet's parameters are here. Dropout layers. Dropout underline 1/dropout underline 2 have 0 parameters, just randomly deactivating neurons. Total params are to 58 million. This shows AlexNet's depth, but the generator and GPU make training manageable. Finally, we compile and train the model. Compile, use model. Compile optimizer equals atom LR equals 0.001, loss equals categorical cross entropy. Metrics equals accuracy, atom optimizer with learning rate 0.001, standard for AlexNet, categorical cross entropy for multi-class, binary here, with 1 hot labels, and track accuracy. Train, use model. Fit generator, train generator, epochs equals 20, validation, data equals validation, generator, fit generator is for data generators, instead of fit, train for 20 epochs, and validate on the test generator. This lets the model learn to distinguish Lishu and Shinkai, with validation checking generalization.